So today in this video, we will not only define the reciprocal lattice mathematically, but also understand its physical meaning. Why do we even need this concept? So let's dive in. In the real space, we know that atoms are arranged in a periodic manner. It is having a well-defined periodicity. This is what we call as a direct lattice. In this, we are having our primitive translation vector as A, B, and C if we are talking about 3 dimension. But here we have drawn 2-dimensionally. Okay. So now when a wave like X-rays, say, interacts with this crystal, what it sees this periodicity, that there is a periodicity in the crystal. The question is, under what condition will the wave interfere constructively so that we can get a diffraction pattern at the screen? We know that the diffraction pattern is formed only when there is a constructive and destructive interference. The constructive interference gives us the bright fringes and the destructive interference gives us the dark fringes. So obviously we need constructive interference to get the diffraction pattern. Fine. So for constructive interference, there is a condition. What is that condition? The condition is that the phase difference between the two scattered waves should be 2 pi times integral multiple of 2 pi. Now, how come this happens? We know, I hope you all know the concept of phase difference. Let me just recall it. If one wave is like this, another wave is like this. So they are having, their crest is meeting with the crest and the trough is meeting with the trough. So the interference will be constructive. Similarly, if we are having the wave, one is like this, another is like this. So the crest is meeting with the trough, so we will be having destructive interference. So for the constructive interference, we need that this phase difference should be the integral multiple of 2 pi. Now again I'm drawing the lattice and I want you to consider carefully that the environment of each lattice point is the same. That means the number of atoms and the number of neighbors and the distance of various neighbors from any specific lattice point is same. For example, I am choosing this as my reference lattice point. So I know it is having these lattice points as its neighbors. So that means this much force it is experiencing. Secondly, if I talk about this atom, it is also having same number of neighbors and at similar distance. So that means the environment of this lattice point is same as the environment of this lattice point. It means if a wave is coming and it is interacting with an atom here, the same wave will interact with another atom in the same lattice and it will behave or it will experience same environment because there is a translation symmetry in the crystal. So if we define the wave function as exponential iota k dot r, where k is my wave vector given by, magnitude of wave vector is given by 2 pi by lambda, that we all know. The wave function will be same at some other point given by r plus capital R. Now this capital R is the translation vector which is given by in some books it is denoted by t also, and it is given by n1a plus n2b plus n3c, which clearly says that if we are moving in the direct lattice from one point to another point like this, we have to move some steps towards x-axis, some towards y-axis, and then some towards z-axis if we are having a 3-dimensional lattice. So putting the values of r here equals to r plus capital R, we get a condition, and the condition is k dot r equals to 2 pi n, where n is an integer. So this condition, that means not all the values of wave vector of the incoming X-rays is allowed, but only a specific values of wave vector is allowed. Now in the further slide, I will show you that these specific values of k are actually what the lattice point in the reciprocal lattice. So reciprocal lattice is actually the fingerprint of periodicity. How can we define it? Just like the direct lattice is telling me the position at which the atoms would be placed, when an X-ray comes and gets diffracted and we get a diffraction pattern on a screen, the diffraction pattern of this X-ray will be like this. That means we will get some bright dots, and I will surely share the link of an animation. It's a beautiful animation. I will recommend you all to go through that animation and you will get the picture crystal clear. That is a very beautifully made animated and animation, and I'm sure you will get the whole concept clear from that. So physically we can say that the reciprocal lattice represents all possible ways waves can interact constructively with the crystal's periodic arrangement of atoms. This is not just abstract mathematics. In fact, every diffraction experiment, whether it's X-ray, electron or neutron diffraction, is essentially probing the reciprocal lattice. The famous Lewis condition and Bragg's law are just ways of expressing that diffraction occurs when the scattering vector is equal to the reciprocal lattice vector. Now what is this reciprocal lattice vector? Just like we were having the translation vector r, we are having a reciprocal lattice vector g, which will be given by h a star plus k b star plus l c star, where h, k and l are just integers, but these a star, b star and c star are reciprocal lattice primitive vectors. Just like a vector, b vector and c vector in direct lattice, we are having a star, b star and c star in reciprocal lattice. But remember, a vector, b vector and c vector are having dimensions of length, but the a star vector, b star vector and c star vector are having the dimension of length inverse, because we are now talking in terms of k space, not in terms of position space. This is our momentum space, and in the direct lattice we talked about the position space. So at the end, I would before going in the mathematics, I just want to recall all the concepts by differentiating between, we are having direct lattice and reciprocal lattice. So we will be differentiating between these two. So direct lattice is having atoms in real space. They actually tells us the geometry, while the reciprocal lattice is telling us the possible wave vectors. Possible wave vectors. So wave vectors is not any physical thing. Possible wave vector that fits perfectly with crystal symmetry, periodicity. Okay. Another difference, if we see, in the direct lattice, this is a real lattice and this is a imaginary lattice. This is not a real lattice, but direct lattice we are having. Then second difference comes out to be the dimension. The dimension here is length, but here the dimension is length inverse. Okay, this tells us the position of the atoms, but this tells us the diffraction pattern. So I hope now the concept of direct and reciprocal lattice must be clear to you all. Thank you so much for your attention. That's it for today's video.